So without further ado, we're just going to have a very quick introduction to us and what we do. And by way of that, we're going to do a case study of how we've engaged on a project. We're then going to do the main part of the presentation, which is a whiteboard session. So hopefully a bit more interactive than the normal PowerPoint. And as I say, particularly during that part, please keep the questions coming in. I'm then going to finish up by a few a little myth busting session. There's enough myths around ground source to go around, so I'm going to hopefully shoot a few of them down at least. And then I'm going to talk about solar and ground source, how the interaction between solar and ground source is a really exciting area of innovation at the moment. Then finally, deeper geothermal that we're touching on, and then ground source as a long-term asset. There will be a bit of time at the end for questions, but as I say, during the presentation is the best time to start dropping them into the chat. So that's what we're going to cover today. And just conscious before I begin that we've got quite a range of experiences, quite a range of different disciplines and talents around the table. And so forgive me if I'm patronizing anybody and stating the obvious, and I'll try to keep it start simple and get complicated as we go along. So hopefully you can all follow. So what do we do? As Joe said, over 20 years of experience in ground source heat pumps. First 13 years of that, some of this in the business were involved in a contracting business. So I've had the opportunity to stand in a plant room and wonder why the thing isn't working, which may be uncomfortable at the time, but it's a great way of learning. We've just reevaluated from Joe's introduction, over 750 megawatts of systems installed per our work up to now. And what we're about is giving substance to projects. So we've got that real world experience. We can give our customers the best possible advice in that regard. Lots of customers, lots of end users, lots of installers use us as their design house, big consultants and so on as well. So a big range of customers that we have. I'm going to give you an example then of how we've engaged on a project. This is a new build justice centre in London, right in the middle of London in Fleet Street, in fact. And we started with an informal early engagement. So that's phone calls, emails. Are we barking up the wrong tree? Is it sensible to even think about ground source at that location? And we don't look to charge for that type of advice. If you've got anything you'd like to bounce off us in terms of a project, please do just give us a call. It's no problem at all. But in this case, we then went on to REBA stage 2. So it's following the REBA stages, this project. And we started with a feasibility study. So that's a desktop geological analysis and a preliminary ground loop design. Main target there was to get some system efficiency modeling, because that's why the system's going ahead, is because of the high efficiencies the system can generate. Very important to point out that even at that early stage, we are using the same design process, the same design software as we use at final design. So we're not going to get any surprises, provided nothing changes in the middle. We then, in this case, went on to REBA stage 3, more detailed ground loop design, quite a lot of structural input in this because the boreholes are actually going under the building during construction, and we've got quite a high rest water level in the ground. So there was quite a bit of structural input there. Talking about project program, project costs, and then finally we specified a set of packages for test bores on the site that were installed. Moved on to stage 4, detailed design, and we're talking about a full system spec. And more importantly, at that point, we get more into design team support. So we're doing more meetings really and supporting, answering questions than we are issuing formal reports. What's next on this project? Well, the main contractor is now on board, and we're discussing how we're going to be involved in the project. Do we stay client side? Do we get innovated over to the main contractor? And how do we give oversight in that regard? So that's a typical example of how we've engaged on a project, and hopefully that helps to show you how we operate. So the main part of what I'm going to do today, I promise you, is a whiteboard session, and I hope not to disappoint. So I'm going to start very briefly with how a heat pump works. Not because I don't think any of you know how it doesn't work. I'm just going to explain how I explain it, as it were. So if I'm asked how a heat pump works, then what I'll start by saying is it's just a box that moves heat from a cold place to a hot place. So it does that. Now, that's obviously a cop-out of an answer. It's telling you what the thing does rather than how it does it. So very simply, how it does it is it manipulates the pressure in a gas liquid cycle to allow allow the liquid to evaporate into a gas at a low temperature, thereby picking up heat and condense at a high temperature, dropping that heat back off. It manipulates that pressure by using the compressor up the top here, and that compressor runs on electrical energy. And I'll come back to that in just a second. There is a final part to the system, which is the thermal expansion valve down here, and that moderates the refrigeration cycle, controls the refrigeration cycle to keep it in the window where it's most efficient and where it's delivering the temperatures that you want to deliver. What it actually is a small pinhole that opens and closes in response to what's going on in the refrigeration circuit. So that's a very high level and very quick overview of how a heat pump works. So how do we then apply that to the ground? And that's really where our interest is in today. So let's look at a heating system here on this side and a cooling system on that side. Obviously, in the real world, you combine these systems. You don't make them separate like I've drawn here. This is just to illustrate what's going on. A few bits of terminology for you. The heat that's coming from the ground is the heat of extraction, the heat being extracted from the ground. The heat being put into the building is termed the heat of rejection. There is a final part of energy, which I mentioned earlier on, which is the electrical energy.
Hey, Chris, sorry to interrupt. There's just something in the chat. I think there's a few people can't see the whiteboard. I can see it.
Okay.
Rich,
shall I stop sharing and start again?
I maybe just stop and start, but if Duncan and Rich and I can see it, then it must be Andy Wood can see it too. Yeah, it must be an issue with their screens. All right.
Apologies
sorry to interrupt.
Well, what we're doing, we're recording the session. So when that's available again, hopefully it'll come up on YouTube and you'll be able to see it better then. So apologies for that.
Hello from Bucharest. Welcome, Mohammed. Thanks.
No, but thanks for letting me know, Joe. I'll do my best to explain it, but it's going to be difficult without the graphics. Okay, so in our heating system here, our heat being rejected to the building is very, very close to equal the heat being extracted from the ground plus the electrical energy. And that's because very close to 100% of that electrical energy through the forces of friction ends up as heat. So your heat of rejection equals your heat being extracted from the ground plus your electrical energy. The opposite is true in the cooling mode. So we're now extracting our heat from the building, the heat of extraction, and we're rejecting our heat to the ground. The same expression runs true, but now our electrical energy is being added to the energy being taken from the ground. And so in a very real way, the electrical energy in heating mode assists the heating of the building, and it hinders in cooling mode, okay? So how do we design these things? The question we ask the design software is, given this heat being rejected into the building, and given the heat being extracted from the building, and we need to understand that on the basis of peaks and also a monthly breakdown of those loads. Ideally, we'd get hourly breakdowns of those loads, in which case we can be very accurate with our design. So given that heat being extracted from the building or rejected into the building, how much pipe do I need to put in the ground to make sure that this system is sustainable in the long term? We also have to add in there the properties of the heat pump, because the ratio of the electrical energy plus your heat of extraction, your heat of rejection, change by different products. So different refrigerants, different heat exchanger architectures, different compressors have different properties. And so given what we're going to do in the building and given the properties of the heat pump, how much pipe do I need to put in the ground to make it sustainable is the question we're asking the design software. I should just say I'm going to talk in the main for the first part about closed borehole systems, but I will come back to talk about other types of systems at the end. So what do I mean by that sustainability? Well, if I draw a graph in a heating only system on an annual basis of the temperature in that ground loop, it's going to start doing this annually and declining slightly. What we don't want it to see is just keep declining indefinitely. What we want it to see is tending to a limit, and that limit needs to be within efficient operation range for that heat pump. If we've got a heating and cooling system, then the graph goes both ways, and we'll get warmer in the summer, colder in the winter. And exactly the same, we don't want that to just get hotter and hotter and colder. We want it to tend to a limit. So that's, in a nutshell, the process of closed loop design for ground source systems. Have we got any questions in the chat yet, Duncan?
Yeah, Joe's actually in with a very interesting question. How did ground source heat pump technology first get used?
A large part of ground source heat pump technology is, at least in my understanding, came from marine technology, and it was the heat pumps in boats and ships and so on that started to interface with the earth in this way. The equations for line source modeling, which is the modeling that we use for closed loop modeling, were written down in the 1920s in a book, seminal book by Karsel and Jaeger. It's a cracking read, really. It is good if you're weird like me. Yeah, that was written down. It was developed a lot, ground sourcing was developed a lot during the original oil crisis in the mid-70s. A guy called Steve Kavanagh took the basic equations and started to build design software packages with it. And today, you know, we've got much more sophisticated tools that we use for design. So that in history is it. But there's systems have been turning up all over the place. I found one in Nottingham that was commissioned in like 1919, I think it was, in a mill in Nottingham, and it was sourcing from the canal outside it. There was one in the Royal Festival Hall put in London back in the when that was built. So yeah, long history of this stuff. Answer your question, Joe. Any more questions for now?
Chris.
Yeah, good to go, Chris.
Okay, all right. So let me just show you what a very typical commercial ground source heating and cooling system would look like. So what we've got here is we've got one heat pump cooling, and that's taking heat from the building and putting it into the loop. I've got a couple of heat pumps shown here heating, and they'll be taking heat back out of that ground loop. So right away, you can see we've got energy recovery going on there, instantaneous energy recovery. And there are a number of different systems that can allow that instantaneous energy recovery to happen. However, the magic of ground source really is when you start to do that energy recovery interseasonally in the ground. We can do heating only systems and we can do cooling only systems. But if we've got some heating and cooling going on, things get very interesting in terms of interseasonal energy storage. Now, I'm very often asked the question, what percentage do I get back? And it could be anything up north of 90–95% of that energy if the ground conditions are right. And I'll show you an example of that right at the end of this whiteboard session. But if, for example, we've got an aquifer down here and there's moving groundwater in that aquifer, you might get no energy recovery whatsoever in that system. So it varies tremendously dependent on the system. Just to give you a bit of an understanding of how these things work in practical terms in the building, I've got one heat pump cooling, as I said, so we've got these two valves here shut and these two valves here open. If our cooling load was to increase and our heating load decrease, then we would now close these two valves here, and we'd open these two valves, and we would reverse this heat pump. So we'd then have two heat pumps cooling and one heat pump heating, and we can flip-flop either way. There's a few considerations in terms of not just how many heat pumps you have, but what size each heat pump is. And a common mistake that's made with this type of system is, let's say, for example, we've got a commercial building with a little, say, 10 kilowatt server room load on there. Let's say this heat pump's 100 kilowatts and 100 kilowatts. And let's say we're in winter, we are heating only, but that 10 kilowatt server room load's still going. So we'd have to turn off that 100 kilowatt heat pump, reverse it, and turn on a 100 kilowatt heat pump just to service that little 10 kilowatt load. So that's going to result in a few things. It's going to be high wear condition for the heat pump. It's like reversing and forwarding your car repeatedly. And it's also going to mean you're going to get a lot of starts and stops, which again is bad for longevity on that heat pump. So it's going to be inefficient and it's going to cause heat pump failures. So in that instance, what you'd probably be better to do is just get a little 10 kilowatt heat pump and connect it up to the ground loop and dedicate it to that cooling load. So that's some of the practical considerations for how you actually put ground source into a commercial building. Anything I need to cover in the chat, Duncan?
We've got a question on calculating COPs, which we can cover off later.
Okay, excellent, thank you. Right, so we are doing quite a lot of this type of building, so multiple residential, both retrofit and new build. There's a load of myths around how difficult it is to retrofit heat pump systems in general and ground source in particular. A huge percentage of our business is retrofit. I've drawn it as a tower block here. It could be a low-rise building, but let's look at this one first. So this is a central plant solution ground source system. So we've got heat pumps here down in the basement. We've got highly insulated pipes going up the building. And we've got in the dwellings heat interface units. And those heat interface units will be delivering domestic hot water into the dwelling and also space heating. Now, domestic hot water, we could be looking for something around the 65 degrees in that domestic hot water. In space heating, we could be doing that maybe as low as 35 degrees C. But because we've only got one network, and because we've got to deliver that 65 degrees, we've got to run that whole network at 65 degrees all the time. Now, the thing about efficiency of heat pumps is the harder they are working, i.e. the bigger the temperature difference between the source here and the load, the harder they're working, the less efficient they are. It's like climbing a bigger mountain, you're going to need more energy to do it. So we are compromising that space heating efficiency, which could be done more efficiently because we've only got one heat network. Another point to make though on this is there is a sale of heat agreement associated with each kilowatt hour of energy delivered into that dwelling. So we've got to look at not just the engineering, but also the commercial elements as well. So let me contrast that then by looking at a distributed heat pump system, very often called an ambient loop, sometimes called a fifth generation heat network, although the definition of fifth generation heat networks is far from universally agreed in the industry. So what we've got now is, first thing you can see is we've got no central plant there at all. We don't even have central circulation pumps on these systems. And that's really important because we've got no central run costs for the system. What we've got in each dwelling though is a heat pump, and that heat pump can turn on to do our domestic hot water at our 65 degrees C, but it can then turn off doing domestic hot water and drop to the 35 degrees I mentioned earlier to do that space heating. So we're not compromising that space heating efficiency in delivering the domestic hot water on the system. However, there's a commercial element to this as well, in that all of the run costs associated with that apartment are associated with the electrical energy being consumed with the heat pump. Now, electricity is a regulated commodity, and so a sale of heat agreement is very different in this regard. You may have an access charge, for example, for the ground loop, but the main part of the run costs for this are associated with electrical energy. So we've got two contrasting solutions here, really, that have different engineering and commercial aspects to them. Technically speaking, almost always the more efficient system tends to be this one. That'll come out more efficient because of that flip between domestic hot water and space heating. However, the network might not get built without that kilowatt hour sale of heat. So we do feasibility studies with both of these being compared, and it comes down one way or it comes down the other. It doesn't always come down for the more efficient solution, depending on the commercials of the project. So that's two examples of how we're deploying these into multiple residential or indeed I'll come back to multiple commercial buildings in a few moments. Anything you want me to deal with, Duncan?
There's a couple of questions which we could touch upon now. What things can cause heat pump failures?
Okay, heat pumps are very robust bits of kit. They're fridges. They're, fridges last an awful long time. They're very robust because they've got very few moving parts, and the moving parts in them tend to be hermetically sealed. So they're sealed inside a gas cycle with lubricants in there. So it's a very long living piece of equipment. What can cause failures? Bad controls. That's probably the most typical problem. Starting and stopping, so short cycling as we call it, turning it on and off repeatedly can cause a problem. Distribution system problems can knock on into heat pump problems as well. But natively, inherently, they are incredibly robust and reliable bits of kit.
And whilst we're on the architectures of high-rise buildings,
Yes.
Space is needed at the surface to install a 5-story building, a system for.
Yeah, I mean, if we've got a retrofit system, then we need space for boreholes in it around that building for a retrofit. In a new build scenario, we could put boreholes underneath the building as well. So yes, there is space requirements. I'm going to come back to drilling deeper to get more out of a borehole in a little bit, so I can talk about that then.
Lovely. There is a question in from a PhD student asking about geothermal piles, and we're going to talk about that towards the end of this the whiteboard session.
Yeah. Let's remind me if you can, Duncan. That'd be super. So, crash course in system hydraulics. About 40% of what we do is geology. About 20% of what we do is that bit I was talking about earlier, how much pipe do I need to put in the ground? And about 40% of what we do is hydraulics. So it's a bigger part of the design, if you like. Now let's look at this example here where we've got 6 dwellings or 6 commercial buildings connected to a single loop. Now what we can take advantage of there is we can assume that not all these buildings are running at the same time. Diversity on that heat network is what we're talking about here, and it's akin to not assuming when you plug in a 4-way electrical adapter, you're not going to have a 13 amp electrical fire on each one. Yeah, that just wouldn't be a reasonable thing to do. So it's analogous to that. The benefit of that diversity is we might save a bit of boreholes, so we might need less boreholes on it. The downside is that this pipe work starts to get bigger, because that pipe work's got to deal with the flow rate of all the heat pumps. It needs to get bigger to keep the pressure drop. If I've got time, I'll come back to pressure drop towards the end and talk about it in a bit more detail. But the more flow you've got, the bigger pipe you need, in short. So an alternative to that, in the extreme example on the other end, would be to break that heat network up. So I've shown it with 2 dwellings here per borehole. And in this case, actually, the collector down here doing the work in the borehole could be actually bigger than the pipe feeding those individual dwellings. So in reality, what we do is a mix of the two. Now, this is a real development. It's finished. And actually, one of the directors of the developer lives there now. Very pleased with his system, he was telling me the other day. So this is a Ken's job. Ken's a heat pump company and contracting company based in the southwest of England. And if I zoom in here, we can have a look at this little crescent. So we've got 5 boreholes here, 1, 2, 3, 4, 5 boreholes, and that's feeding these 10 dwellings here. So that's one heat network in and of itself, and that keeps that pipe sizing down. Interestingly though, if we look at in a bit more detail up here, we've got array 28 here, and it's got 4 boreholes. And we've got array 29 up top, and it's got a couple of boreholes. They are not in hydraulic contact, so there's no hydraulic contact between those 2 heat networks, but they are close enough together to be thermally interfering with each other. So when we're designing these systems, we can't just design each heat network in isolation. We've got to take a view on the overall system as well. So the design of these things, when you've got multiple arrays on a single site, is actually quite interesting and very challenging to do. So it's something that we've pioneered in the marketplace over the last few years. Any thoughts or questions coming in, Duncan, while I take a mouthful of water?
Some very good question. Could a ground loop be reheated by air?
Yes, it can be. I've only done it on a couple of occasions where you put a dry air cooler on a ground loop and you use it not just to reject air off that ground loop, which I'll talk about again in a minute, but you can actually suck heat out of the system. So yeah, that can absolutely be done. I'm going to talk also about the hybrid of solar and ground source in a minute as well. And there's an element of air heating involved in that as well. So yes, it can be done. Any source of heat, we love it.
Yeah, absolutely. Any source of heat you can put back into that borehole collector system helps everything.
Absolutely. This is a good example of that then. So we've got a mix of maybe small commercial and larger industrial commercial buildings on a single ground loop. So let's say this is a supermarket that's putting heat into the ground, and we maybe have some dwellings taking heat out of it as well, and so on. So the more diverse loads we mix on these networks, the more effective they become, more efficient they become. And actually, you might need less loop to do the same load because you're putting something back in. There's a thing going through at the minute on heat network zoning legislation. So that might give local authorities, at least in England and Wales, I don't know if it's going to go out to Northern Ireland and Scotland yet, but it'll give them the power through planning to require some kind of requirement to connect to these heat networks as they're built out. So it becomes a very powerful concept. And what you can actually do beyond that is you can start connecting these heat networks together. So we might have 2 ambient heat networks here, and we put a heat exchanger between the 2, and heat will naturally balance between those 2 heat networks. We could also consider any other source of heat, as I was saying earlier on. This might be a waste to energy plant. It might be a conventional second, third, fourth generation heat network. It could be an industrial process, for example, and we can just put heat into that low temperature network. Now, the beauty of this is we can recover heat, really, anything above 0 degrees. we can recover heat into that loop. So it's incredibly efficient and effective at recovering those low grade heat from those kind of sources. Anything coming in before I start to talk about other types of ground loop, Duncan?
We've got a few questions based, if we go back to the Kenza design.
Yeah.
Great question in from Andy at Seraphy.
Hi, Andy.
Hi, Andy. Yep. How do you determine the distance wells should be separated to negate interference? And given Andy's geological background, I think he'll be quite interested in this.
Yeah, it's really interesting. So if we've got a heating only system as this is, we would see interference between the boreholes. Even at 20 meters separation, we would start to see interference in the between those boreholes. When you're below 16 meters, it starts to ramp up. And if you were to do something like this on 6 meter spacings, you'd have an awful job getting a sustainable ground loop out of it. If you've got a heating and cooling system, however, at those lower, narrower separations, you can recover heat more effectively. So it's a balance between, is it heating only, is it heating and cooling, and so on. But also we've got the practicalities of it. You know, you can see on this site, we haven't got an awful lot more space for boreholes. So we're kind of limited to what we've got on there. You see, we've avoided the carriageways here as well, because they were going to be adopted by the council. So there can be legal constraints as to how much space you've got. So anywhere between 6 meters and 20 meters is the answer to that. And it very much depends on the balance of heating and cooling loads and also the geology. If you've got moving groundwater, for example, you could pack them together much more.
I was going to say just that about the moving groundwater.
Yeah, it's really important. Great question, Andy. Thank you. Right, so I've talked so far about closed loop vertical boreholes. Now let me just describe what one of those actually is. So it's a very simple hole put in the ground. It's got very little structure to it, and then we hopefully can just drill it open. We're then going to put a U-tube of pipe in there, polyethylene pipe, and we're going to fill that U-tube up in most cases with our grout material. The boreholes here are quite narrow diameter. They're only about 150 millimeters, can be even less, can be more. And they typically go from 100 to 300 meters deep. That's the kind of depths that we tend to see. So that's vertical boreholes, ubiquitous really for commercial ground source. They are, just as I say, a closed loop of fluid also. There's another alternative, particularly when you're on a smaller scale, which is horizontal trenches. And I tend to like to do these types of ones with 6 pipes, as they're called. It's 3 loops in each trench, and the loops just go in like that, and we backfill between the layers. You will also see in the magazines and so on slinkies. That's quite a lot of pipe in a small area in general, but so I tend to prefer the horizontals. At the commercial scale, really schools, those kind of places where you've got playing fields, that can be a useful place to deploy that type of technology. There is one other type of closed loop system that's very much worth talking about, which is when we've got some surface water. So we can install a heat exchanger in a body of surface water, and we can take heat out of that body of water and we can put heat back into it. And provided we are balancing what we're doing to the lake with the natural gains and losses of heat that occur, then we've got a sustainable system again. So our main gains are via solar gain, and our main losses are actually via evaporation. So the evaporative losses off of that lake. Now, these systems are incredibly powerful systems, and they can't do huge loads. They're particularly suited, for example, if you've got a massive new build housing development, thousands of houses, if you can incorporate some lakes into your landscaping plan, then something like that can be a much more economic installation than boreholes. So that's the 3 main types of closed loop. I will come back to loops in the piles and the foundations of buildings in a case study in just a sec.
Cool. Quick question while you're on that, Chris.
Yep.
Then are all boreholes grouted, and what grout is used? And is there a cost benefit by grouting?
Yeah, okay. So not all boreholes are grouted. In Scandinavia, they very commonly hang pipe into the boreholes by a sealed collar. And they do that because the boreholes are full of water. That's a very common solution there. The seal is just providing a sanitary seal on the system. Another common solution that I've just spec'd on a job in London, actually, is where you fill the bottom of the borehole. Let's say you've got a rest water level around here. You might fill the borehole with gravel to that depth and then put a grout plug in on top. We do have a requirement, however, to make sure we've got a sanitary seal in that borehole, just like a water well for you geologists. So there are other options in there. There are costs associated with grout. Yes, there are. The main grout used is a bentonite material with a high silica sand content. So normally a 1 to 5 mix of bentonite and silica sand. And there are a lot of specialist products on the marketplace with enhanced conductivities. You don't want to use a low conductivity grout in these systems.
Does the pipework ever leak?
I've been responsible for something like 50,000 boreholes in the 20 years that I've been involved in ground source. During installation, you get pipe failures and they're remediated at installation. So you're testing as you're installing. That absolutely does happen. But post-installation in those 50,000 boreholes, I know of only 3 that have failed. And they're actually all in one project. And we believe the coal mine that we drilled through, and you were drilling through it, the coal mine has either collapsed or gone on fire, and it's destroyed 3 boreholes. So it's a very unusual post-installation for that installations to fail. Great questions. So there's another type of loop, which is open loop. Now, when in open loop, what we're doing is we're taking water from a body of water. I've shown it here as an underground aquifer. We're taking it out to the ground, warming it up or cooling it down and putting it back into the ground again. And then over time, that water will propagate over between the 2 boreholes. So it is a loop, but it's got an open element to it. Now, this is a different animal really from closed loop. In closed loop, what's inside the loop, we've put there and we know exactly what that is. Here we're dealing with the water that's open to the environment. So we've got water quality to consider. Now, if you look at some of the aquifers under London, for example, very, very clean water there. So your maintenance cycle for your pump and your heat exchanger might be 10 to 12 years. If you've got some of the aquifers up in or maybe even a coal mine, for example, you could be talking about maintenance on a monthly basis for that type of water. So it's a different beast. And also there are statutory licensing requirements in much of the world for this type of technology as well. In England at the minute, the licensing process for an open loop system is taking 12 to 16 months. So it's quite a significant endeavor. So my rule of thumb is if you can do closed loop, technically and economically, then you should do that because you've got that long-term maintenance and not exposure to licensing. You've got that benefits there. However, open loop is a brilliant technology, particularly when you're talking about compact sites, when you're talking about high heat loads and so on. It can be your only option, really. So it's very much worth considering, and we specify and install both. So I did promise you another case. Sorry, Duncan.
Yeah, got a question that came up during the closed loop discussions, but is relevant to open loop. So if you have a groundwater flow and a groundwater well in neighbouring, can you tell how far you have to be from the well to avoid a temperature drop in the well during the year, even in a balanced system?
You can model it, yes. It's very complicated. And when you start looking at groundwater flows, there are geologists around the table who will know much more about that than me. Generally speaking, you're talking about finite element analysis, which can be quite challenging, and the accuracy of which it's not perfect. So you've got challenges and considerations there. But yeah, we are increasingly being asked to provide finite element analysis models for closed loop systems. Now, I'm actually consulting with the Environment Agency at the minute on on open loop systems. I'm consulting with the Environment Agency at the moment on receptors for problems with closed loop systems as well. So it's quite a complex field. What I can't say is closed loop modeling, if you've got no moving groundwater, is very precise. When you start to add moving groundwater in there to it, then you lose a degree of precision. And again, open loop modeling is a little bit less precise. So a lot to that. Maybe that's a subject, Joe, for a future session. Be a good one. Okay, so this is a hybrid ground source system. This is a building called One New Change. It's a Lancet building. If you imagine standing on the dome of St Paul's Cathedral in London and looking east, it's at your feet. It's got 3 stories of offices, 3 stories of shops and restaurants. Then it's got 3 stories of offices on top. It's got a lovely rooftop bar, great place in the summer, particularly to have a drink in the evening. And what we put our brief in this building was do as much as we possibly can with the ground. Okay, so there are unusually big and deep piles on this building because of the structure. And what we did was we put loops in that piles, and that is our interseasonal energy store. And that's taking advantage of the properties of the London clay. So the London clay is at high density, high specific heat capacity, low conductivity, medium. So we're using that as our energy store. It stores energy brilliantly, and it's in that 95, 98% energy recovery regime. So what we're doing, it's a bivalent system, this, so there are other heating and cooling plant available to us. So we can schedule loads on and off of that, on and off the loop to manage the loop temperature in there. We can also manage that loop temperature by turning on our well pumps here. And it's exploiting the properties of the chalk, which I'm sure that the geologists will know. In the cracks and fissures in the top, say 20 meters of that chalk, water is there. And so we can use that water to then either increase our ground loop temperature or decrease it. The net effect of all of that is that we are managing this closed loop in the 20 to 25 degrees bound. Not all the time, but that's the majority. And the reason we're doing that is because if you draw a graph of the efficiency of the heat pumps in question, the heat pumps installed, the coefficient of performance, you were asking for a definition of coefficient of performance, weren't you, Duncan, earlier on? So COP is very simply the energy that's being delivered into the dwelling, so what I'm interested in, divided by the electrical energy that's being consumed. So it's our heat of rejection divided by our electrical energy, and that's our COP, coefficient of performance. I'm going to come back to the difference between seasonal COP and COP in just a minute. So back to my graph here, for the specific heat pumps involved, if you draw a graph of their heating and cooling efficiency, they cross over at that point around that 20 to 25 degrees C point in there. So we're optimizing efficiency of our heat pumps with all these different methods. So it's a really efficient system. Last time I saw data on this, it was achieving a seasonal COP of 6.8 in cooling and 4.8 in heating. So massively efficient system interseasonal. Any questions worth dealing with before I leave the whiteboard?
Question from Joe. Do these systems have lower running costs than traditional fossil fueled ones?
With the fuel prices we are now seeing today, almost universally, yes. Certainly if you've got a heating and cooling system, there are some customers of ours who've got legacy very low gas prices that they've still got access to, and they're waiting until the end of the contracts probably before they do an installation. But yeah, almost universally we are saving significant sums of money now with these systems.
Can you install closed loop systems in groundwater source protection zones like in some chalks?
Yes. Simple answer. Yeah,
You can even install some open loop systems in source protection zones, but there are a few extra hoops.
Yes, a few extra hoops to jump through in that one. But yeah, closed loop, generally no problem. But we do have to consider a bit of detail in the method statements and risk assessments.
And how feasible is a river as a source?
Very feasible. Yeah, I should have said in my open loop section here that this could be ocean, could be river, could be canals. You are dealing with untreated water, remember. You've got to access that water as well, so you might need some kind of construction to access that water. Power stations are by the sea in the main because they cool to the sea. You know, so heating and cooling from surface water with open loop technology is very well understood. So yeah, super questions. Thank you.
Yeah, and while we're on One New Change, will there be any update for the guidebook covering more aspects of geothermal structures issued by the GSHPA?
We've not got an update in the, I say we because I sit on the council of the GSHPA. Joe, you mentioned that, sorry. But we haven't got an update planned for the thermal pile standard at the moment. We're just about to issue an update to the vertical borehole standard, which I co-authored with others during the last year or so. But we've got quite a bit to do with that first. The next standard is going to be a thermal transfer fluid standard, which is what's inside the loop. We're going to have a standard for that. And then we're probably going to address the elephant in the room, which has been there for a long time, which is an open loop standard next. So thermal pile standard could be a couple of years away from an update from that.
Lovely. Thank you, Chris.
Okay, right, back to PowerPoint now. So let's deal with a few myths. First of all, ground freezing is something we hear all the time. We absolutely do run at negative temperatures in the fluid inside ground loops. So we've got propylene glycol in there. But if you are seeing adverse effects on structures at the surface or whatever due to what the ground loop's doing, then that loop is just not well designed. It's an unsustainable loop. I've got some horror show pictures of somebody put some loops in the patio, in the sand under their patio. You know, first winter, that's like, you know, it's just buckled and heaved. So if you're seeing any negative temperature, sorry, any negative effects due to that ground loop, it's inadequately designed. It breaks my heart how many reasons I hear that ground source can't be done. And it's mainly in your mainstream consultant reports. You see it quite a lot, unfortunately. And you can't do it because we've got hard rock, because we've got soft rock, because we've got archaeology, because we've got source protection zones, you mentioned earlier on. All these reasons why. The truth is that a lot of times ground source is ruled out by mainstream consultants because they don't understand it. And that's kind of why we set up our business, as to provide that information as backup to the consultants. Colleague and friend of mine in Canada, Ed Lawrence, he did some work with a university over there, and they concluded that something like 80% of viable ground source projects get written off at feasibility study stage by poor knowledge, poor application of rules of thumb, for example. I saw a multi-megawatt business park ruled out by a consultant because they couldn't fit enough slinkies in there. There's no way you're going to do a multi-megawatt system with a horizontal system. So, you know, those kinds of things. It's worth a note about reliability and complexity. A lot of people tend to overcomplicate these systems, and that has an adverse effect on reliability. So you do have to really consider any complexity you're adding into that system. On the other side of it, reliability is really one of the big strengths of ground source. It can be made much more reliable, significantly more reliable than conventional technologies. The collector is buried, so you know, damaging it is much more difficult, and so on. So there's a balance between reliability and complexity. If you get that right, you should absolutely have the most reliable system you can possibly get. Touched on archaeology, it's no problem really. Miracle loops is another one. I'll get probably once or twice a year company coming to the marketplace and sell it, saying, you know, our ground loop with this coil and that pipe in it and so on will give you 6 times of what anything else in the marketplace will. What I can absolutely tell you is that if the ground won't give it to you, you cannot take it out. And so that might be true if you've got a very highly conductive ground condition, but in the majority of cases, there's no way one loop is going to have a massively significant difference over the other loop architecture. I mentioned seasonal COP and COP. COP is a spot coefficient of performance. The rating point for air source heat pumps is 735. So that's 7-degree air temperature, 35-degree load temperature. The rating point for ground source is 0.35. Now remember, I talked about the lift that's being carried out by the heat pump. Ground source, if you just do a straight rating point comparison, is going to come out less well than the air source in some cases. So you absolutely must use a seasonal COP, which is the annual heat delivered divided by the annual electricity consumed. And that's a much fairer comparison. And to do that, you need to understand not just the air temperature, but the humidity in the air. And in the British Isles, we've got, unfortunately, we've got that climate that never gets very cold. It's always a bit wet in the winters. And so you get defrost cycles happening on air source. So you're getting frost forming on the coils of air source, which needs to be defrosted. So that dramatically reduces the efficiency of the system. For ground source modeling, obviously we don't have the frosting problem, and you need to do a dynamic model of that ground loop temperatures. But we can actually do it a bit more accurately than air source can be modeled because of that variation in temperature and humidity in the climate. So you must use a seasonal COP rather than a COP. Life cycle costs are really interesting. At the moment, we are seeing projects comparing air source and ground source. If you've got your only interest really is that initial cost, that installation cost for the system, then go air source or go direct electric if you can get away with it and you don't mind your tenants paying loads of money to, or your homeowners paying loads of money to heat their homes. But if you've got any view in the long term, then ground source, even in an 8 to 10 year cycle, can have life cycle costs half of what air source can have. Lots of nonsense about space required, as I touched but earlier. And then finally on the myths, there is a preoccupation in government for delivering decarbonisation on a house-by-house basis. If you do ground source on a house-by-house basis, it's going to be massively expensive. There's no doubt about that. If I do my borehole this year and my neighbour does his or her borehole in 2 years' time, that's 2 mobilisations. It's massively expensive. So we've got to stop thinking about house by house and start thinking about street by street and town by town. And we're actually doing our first installations now on that basis, where we're putting boreholes up the middle of the street and offering connections to homeowners either side. So it's a radical change in the marketplace. A couple of slides left, and then we can wrap up any questions, unless there's something pressing in the chat. Duncan?
I'm collecting a few questions for you, Chris.
Okay, good man. Right, so solar and ground source. Let's finish the next couple of slides, unless it's something really relevant. So we've got a ground source heat pump system here with a ground loop there, and we could put a PV panel on the roof, and that PV panel will collect heat, turn solar energy into electricity. So you've got a hybrid, but it's a little bit of a trivial one, in that you're generating electricity from one and you're consuming that electricity by the other. A more interesting hybrid, however, is when you start to look at solar thermal, and even if you start to look at solar photovoltaic thermal. So it's a solar PV panel with some solar thermal collectors in behind. Now, what we can do with those solar thermal collectors is put a little heat exchanger in our ground loop and connect it up. So we're actually now recharging that ground loop with solar energy. And it's really fascinating what goes on with this. So I've got a system that's been installed for a few years and monitored in Cardiff, and it's achieving a seasonal COP of 5.5 off of that system. So without that solar assist, it's going to be around the 4, a massive increase. But also, we've got a couple of really interesting effects. Because we are cooling that PV panel, we're actually significantly enhancing, I reckon about 25%, enhancing the electrical generation as well. And back to the question on, can we use the air? We're actually also getting some conductive gains in from air temperature on there. So if you look at the solar tables for the area, we're actually capturing more than 100% of the incident solar radiation on those by those panels because of that additional conductive loss. When I did the sums on that as a physicist, I saw a number bigger than 100%. I kind of thought I was deluded, but we worked it out in the end.
Chris, can you just elaborate on the benefits of thermal ground recharge?
Yeah, I mean, so we've got a couple of benefits. So we can start to avoid those minimum temperatures, so keep that temperature higher. And actually on these flats in Cardiff, we're able to keep that ground loop temperature to that 20 to 25 degrees again, back to that magic crossover point. So we've got a warmer ground loop, we're recharging the battery, and we're able to deliver much higher efficiencies as a result. Is that what you were thinking of, Duncan, or do you?
Yes, and we can also talk about the CapEx benefit potential.
Yeah, absolutely. So yeah, if you can design in solar recharge, potentially you could get away with less ground loop and have a similarly efficient system. So there's quite a lot to that as well. The data we're getting off of the job in Cardiff shows that you can have your cake and eat it, in essence. You can have less ground loop and a more efficient system as well. So traditionally in ground source, as I mentioned earlier on, we've been around 100 to 300 meters depth. To get to high temperature, so electrical generation in the British Isles, you're looking at, say, 5 to 7 kilometers depth to get to those high temperatures required for electrical generation. But increasingly, we're looking at these middle depths here, 800, 1600, 2 kilometers, and deeper. So those kind of middling depths. And what we're doing is we're borrowing technology and maybe even borrowing assets from the oil and gas industry. So there are a number of onshore oil and gas wells that could be repurposed to become heat generation assets. Rather than being decommissioned at quite big cost, multi-million-pound cost, they can be effectively recommissioned as heat generation assets. And also using more oil and gas well drilling technologies to access those middle depths. The other benefit of this is, if we've got a limited site, we can get more out of each borehole. So we're able to access more and more dense developments. So finally, ground loops as an asset. This is one of the most exciting developments in the industry at the moment. Ground loops very much are the new gas pipes, the new electricity pipes, the new water and broadband pipes. Now, how they are installed, when the gas pipe was installed in my house before I bought it, the homeowner didn't pay for that. They effectively, like buying a mobile phone, have leased it over a long period of time. So by looking at ground loops like that as that long-term asset owned by a third party and sweated over 30, 40, 50 years, we can really start to see that ground source can become as economic as the alternatives in the short term, not just the long term. So imagine we're going along to a developer. They are trying their best to get through planning with direct electric, because that's the cheapest thing to do. Probably won't get away with that, so they're looking at air source. We can go along to them and say, we can put in a ground loop asset for you that will be owned and operated by us in the long term. And actually, because the heat pump's internal now, not external on a plinth, it's a cheaper installation as far as the developer's concerned. So it's really revolutionising the marketplace at the minute. I'll drop out of screens here so we can see people, and we will take more questions if we can.
Yeah, I got a few questions collected. I think it was the same person asked both of these questions. Who is the most influential person, client side, in awarding a geothermal feasibility study? And on a new build project, who is the most influential person, client side, in awarding general geothermal work? So who should be targeted?
That's really interesting. I suppose the decision makers tend to, when you're talking about deciding that this is going to go in, you're obviously dealing a lot with the financial people in the project. So you're looking at financial justification for the projects, but you're looking at signing off feasibility studies. Most of ours get signed off by the project team and the consultant engineer. They'll say, we need specialist input in this regard. They'll recommend that to the client, and then between them, they'll agree to engage us. So that tends to be how we tend to get involved in the marketplace.
Should we have a moral obligation to grout geothermal boreholes to prevent surface contaminant pathways?
Absolutely. So if you are creating a contamination pathway, or for example, you're connecting two dissimilar aquifers, then the legislators won't like that. That would be considered polluting. So yeah, absolutely. In many cases, doing what I described earlier on with gravelling boreholes could be unacceptable. I don't like to say that we should rule out gravelling boreholes. For example, the carbon content of the embodied carbon content of a gravel borehole is significantly less than a grouted borehole. So there are benefits to it. But geologically, you've got to be very sure you're not going to create a contamination pathway, as I say, either from the surface down or between dissimilar aquifers.
Lovely. I think we've got a hand up if that person, if Michael wants to unmute himself and ask the question.
Conscious of time, so if Michael manages to, no, he's taking his hand down, so we'll get it over.
Okay, no problem. Do we work in the Republic of Ireland? I can answer that short yes.
Yeah.
We've done a number of projects in the Republic of Ireland. Question and statement. I met with Tony Amos in Switzerland last year, and he told me there's no official guidebook. Do you see a future guide that can help contractors rely on?
Well, we've got the standards, the Ground Source Heat Pump Association standards, which are some of the best in the world, actually, I have to say. And they cover horizontal systems, energy piles, thermal foundations, vertical borehole systems. They've also got a guide to sustainability as well, which was originally authored by the Environment Agency, and that's been adopted by the Ground Source Heat Pump Association. All the standards are available, so they are very good. Should closed-loop installations be regulated? I do hope not, but we do need a bit more registration of them, I think. What I'm talking about in the Environment Agency at the moment is if you are adhering to the appropriate standards, then regulation should not be required. If you're going outside those standards, then potentially it might be a good idea. So yeah, it depends on what you're doing.
Can the solar recharge also be rainwater recharge?
Yes, you can use both waste water from dwellings and you can use rainwater to temper ground loops. Again, you're dealing with untreated water there, so you've got concerns for heat exchangers. There are off-the-shelf solutions for wastewater energy recovery, and obviously recovering that to a ground loop is a much more effective way of heat recovering than it would be, for example, you're trying to heat water with it. So it's an interesting system that I have worked with a couple of times in the past.
Lovely. And Chris, in your opinion, do you prefer solar thermal or dryer cooler recharge?
Solar thermal. Solar thermal, yeah, it's more universally applicable. The reason we put dry air coolers mainly on loops is if we've got a cooling imbalance, so we've got much more cooling demand, and what we can do is run that dry air cooler overnight to temper our ground loops for next day's operation. So my ground loop's above 25 degrees. I'm going to run it for a couple of hours at night to then pull the ground loop temperature down to 20. Turn my dry air cooler off and then hide away in the ground during the day. So that's the main reason you put dry air coolers on ground loops. But as I say, they can be used for heat injection into the ground loop. But you get the same problems you get on them as you do with air source, in that you get frosting on the coils of the system because you've got water condensing onto them and then freezing up. So you've got to have a strategy for that as well.
You've pretty much just answered Andy Wood's question in that can GSHP systems be used efficiently as cooling solutions in the tropics where average daily temperatures are 30 degrees?
Yeah, absolutely. We're being increasingly asked actually for work in the Middle East and hot climates. There are systems installed all over North America, to give you an example, and you know the extremes of climate that exist there. So yeah, absolutely, it can be done.
Cool. And question from David, how is this different to district heating?
Well, when we're talking about your ambient loops or fifth generation heat networks, as we call them, and we're connecting multiple buildings together, really it is a form of district heating. It's just that ground loop is now, it's not insulated pipe, it's running at a much lower temperature and it's extracting energy as it's going. You've also got distributed plant as well. So really it is a district network that we're talking about when we're doing these. And in fact, we're working really hard in the lobbying front to make sure that that continues to be acknowledged, and is the case that these are district heat networks, yeah.
Is it possible to extract heat from decomposing waste in landfill?
Yeah, absolutely is. Challenge you've got with landfill is it's the variability of it. And yes, it's decomposing, so it's hot. But the variability as far as drilling, as far as making sure you're not breaking any seals, because landfills tend to have like a lining at the bottom, clay often at the bottom of them, to avoid any seepage into aquifers and so on. So there's quite a lot of engineering involved. A common solution I have actually used is to put horizontal systems under manure piles and things like that. So that's a common solution that works really well on farms and things like that. So yeah, you know, you can get ground temperatures up to 30 degrees shallow under a pile of water.
The same person who asked that question said the ground source heat pump installed in 1990 to heat a municipal pool using 20 degrees water is still in use.
Fantastic.
In a geothermal aquifer.
Fantastic. That's great.
Do we have any knowledge or experience of successful micro borehole geothermal in East Antrim?
Well, I've been involved in projects all over the island of Ireland for many, many years, and I'm sure there are some there. Micro borehole installations I've been less involved in, although I have seen several architectures involved. The thing is about closed loop boreholes to 100 to 300 meters deep, it's really robust technology, and it tends to be very applicable, so it tends to be used. But I'm not saying it's a bad idea by any stretch of the imagination, by the way. So yeah.
Keith has mentioned, would heat extraction from landfill decrease bacterial activity though?
It would, yeah, almost certainly it would. So yeah, there are all sorts of implications. I'm not an expert in landfill, I'll be completely blunt, but yeah, I have looked at it before. I've not actually installed a project in that way, but yeah.
Cool.
I'll carry on, Joe, for a few minutes to take more questions if you are.
Yeah. Once we finish out on the questions, we'll round it up, but people can leave as they want. But I think we're nearly there anyway. There's maybe one or two more.
Okay, super. Good.
What software do we use to model our systems, Chris?
We primarily use GLD by Gaia Geothermal, ground loop design. It's based on Steve Kavanagh's equations he wrote down in the 1976, I think it was. It was first launched around 2000, and I've used it for all the time in between. I trust it. It's a very good package in terms of its flexibility. You can get it to do all sorts of things that it wasn't necessarily designed specifically to do. I also use EED, which is Earth Energy Designer, which is a consortium mainly based at Stockholm University. So that's quite a useful package. There are differences between the design packages. One of the things I like to see in a design package is an active heat pump model. Not all of them have that. And that's really important because the ratio of the heat of extraction, heat of rejection, electrical energy is really important to modeling, not just how much pipe I need, but also getting an accurate seasonal COP model. So that's why I tend to prefer GLD. GleePro also does, it's another package I've not had so much experience in. It does seasonal COP modeling as well. There are another couple around the world as well. And then there are a lot of heat pump manufacturers have their own, what they call design software. In the main, and I've not been able to find one that isn't, just a lookup table, and I really don't trust lookup tables as far as ground up design is concerned.
Can piles under buildings in landfill not break seal? So that means can you use piles under buildings on old landfill fill sites?
I would be reluctant, to be honest, but if they are piling into a landfill, obviously the structural people and the environmental health people and everything else will know what they're doing in that regard. We could certainly design pipes to go in it. That wouldn't be a problem, but I certainly wouldn't get involved in the implications of doing that.
That's the lot of the questions.
Fantastic.